In this video, we're going to look at regression output. And so let's actually look at some real data. I made this data myself. The NBA season is coming up fairly soon, and I'm getting antsy. It's been a while without basketball. And so what I did here is I made a fictional basketball team that's played 20 games. Okay, it isn't related to business, but you know, this time, let me off the hook. We've got a basketball team that's played 20 games, and I've got two variables here, shooting percentage and points scored. And here we're going to use shooting percentage as the independent variable. Shooting percentage is going to be the predictor variable that predicts how many points are scored in the game by the team. So one team, we've got 20 data points, 20 games measured so far. We've measured the shooting percentage for each one of those games. This is the whole team's shooting percentage, and we're looking at the points scored in each one of those games. And so, you know, we can make some predictions right off the bat. You say, well, probably if a team is shooting better, they're scoring more points. And you'll see that basically holds true. But it's again, as with all regressions that make sense, it's not going to be a perfect relationship. There's other factors, how many turnovers the team has, you know, how well they shoot their free throws and things like that. So, you know, how the pace of the game. So it's not going to be a perfect predictor, but you'll see that there's, you know, in this, I made up this data, but actually there's a fairly predictable relationship between these two variables. Before we actually get into running a regression, what I'd like to do is just make a scatter plot of this data. So let's do that here. I'm going to go ahead and highlight both of these and go to Insert, Charts, Scatter Plot. And that doesn't exactly look the way I was hoping it would look, but maybe that was predictable too. I need to format these axes and sort of zoom in on the data that I want here. So let's do that. I'm going to right click, New, Format Axis, and I don't know, let's make this a minimum of 70 and a maximum of 120. All right, it's already looking better. Let's do the same thing for the x-axis. And we'll go 35 to 55% shooting, because that's going to cover all of our data. And already everything's looking better. Now, I'd actually like to put a trend line on this. I'd like to see what regression is going to look like here. So let's do that. Click here, click on Design, Add Chart Element, Trend Line, and we're going to add a linear trend line. And it does look like a roughly linear relationship. This will work. It looks more linear than any other type of relationship. And actually, Excel's nice. It'll allow me to do even more fancy things. I'm going to format my trend line here. I'm okay with the dotted line, but what I really want is for the regression equation to display on the chart. And I'm going to go ahead and ask it to display the R-squared as well, and I'll explain what that is in just a moment. So the first thing I want to point out here, well, everyone can see this equation. We have an equation. In fact, I'm going to move everything over, and let's see if we can get it all on one page. All right, so I've got an equation here, and that equation is y, meaning points scored, is equal to 2.6144x, x being our shooting percentage, minus 19.572. Not enamored with my handwriting here, but we'll work it out. That's our equation. And there's some funny things you might notice about this, and this is often true with regression. Our y-intercept here is negative 20 points, negative 19.572 points. That doesn't really make sense. I mean, if a team shot 0% from the field, they aren't going to score negative points. They might score 0 points or you know, 1 or 2 based on free throws, but basically they're never going to go into the negative range. So does this make sense? Yeah, it still works. The reason that this happens is because we don't have data. We don't have data points that measure all the way down to well, actually, I formatted our axis, so we only go to 35%. But we don't have anything that goes down to like 10% or 2% shooting. So sometimes it works out this way. And that doesn't mean this is a bad prediction. It is a good prediction. we would actually not use our regression to predict, and this is actually an important point, you don't use a regression equation to predict points outside of the range of data you already have, because things can get kind of wonky, when you go outside the range of data that you have. You don't know. It might be linear for a ways, and it might not be linear later on. So it's only, this regression equation is, if you're going to be cautious, really only good when the team is shooting between 39% and 52%. It can make a prediction anywhere within that range, but if the team shoots 60% from the field, all bets are off. My guess is actually they probably wouldn't end up scoring as many points as the regression equation would put out there. It might be an indicator of, I don't know, something else. They may be taking a lot of time on their shots, or who knows. Okay, that's our regression equation. Now there's something else that you may have noticed on this chart, and that is this, r squared equals 0.7759. What the heck does that mean? Well, r squared is something you're always going to get in regression. And by the way, we haven't even really, what Excel just did is it ran the regression for us. But there's more sophisticated ways to run regression where we're going to get even more data. And that's what we're really going to spend the bulk of this video looking at. But this is, this is the real regression. You'll get the same equation when you use more sophisticated methods to get it. And r squared is sort of the second most important part of a regression, probably. You have your basic equation, and then you have your r squared. R squared says this is the proportion of the variation in y that is shown by the independent variable, that is predicted by x. The percent of, or in this case, it's the proportion of the variance in y that is predicted by x. More specifically, and to bring it back to terms you already know, r squared, in this case, r is the correlation. So if you took the square root of r squared, you're going to get the correlation between these two variables. So it's all sort of interrelated. The correlation, which you already know as a measure of the relationship between these two variables, r squared is the square of your correlation, and that just tells you this is the percent of the variance in the dependent variable that is predicted by the x variable, by the independent variable, that is explained, I shouldn't say predicted, that is explained by the independent variable. So in this case, 78% of the variance in points scored is explained by your shooting percentage. Hopefully that makes sense. It's sort of like, it sort of shows the predictive power of the regression. That can be debated, certainly, but it's a simplified way of thinking about it. Sort of, the higher the r squared, the more predictive power your regression has. All right, so let's actually get to running a regression and looking at the results. The good news is, now we're using Excel, but the good news is that your output for a regression is going to look pretty similar. It's certainly going to have the same numbers, and it's going to give you the same information basically no matter what program you're using. If you're using Excel, or if you're using statistical software like SPSS or R, it's going to give you pretty much the same output. So if you are not using Excel, you should be able to follow along with what we're doing. But I'm going to use Excel, and there's actually multiple tools you can use in Excel to give you to perform a regression. I'm going to just use sort of the standard, which is the data analysis add-on, I should say. So I'm going to highlight my information. If you were using the regress add-on, you would need to name your data, which you can do under data. You have to assign, you do it under formula. You go to name manager or define names, and so you'd call this column shooting and this column points scored. But since we're using data analysis, I don't have to do that. So I'm going to select a y range, that's my dependent variable, and I'm going to select an x range. And since I selected the column, let's try that again, y range, click in here. Since I selected my column headers, I have to check this box that says labels. In other words, yes, there are labels in my data. And, oh, what the heck, we'll go we'll insert confidence intervals, and I'll explain that in a moment. And we're going to put our output range right here. Okay. Ugh. I'm going to have to delete this thing. So goodbye scatter plot. Served us well. And let's shrink some of this other stuff down a little bit. Make room, make room. Here's our regression output. If you can't see all of it, that's okay. We're going to focus on sort of this part in here to start with. First of all, I want to point out our coefficients. Coefficients are what make up the equation that we just got. So you can see that we have two things listed here, intercept and shooting percentage. Shooting percentage being our independent variable and intercept being our y-intercept. The coefficient for each is what we got a moment ago when we put a trend line to our scatter plot. I wrote it down so we can call it back. There it is. 2.6144, 2.614427 is okay. It's a few more decimal places, but it's the same information. Times shooting percentage plus negative 19.572. That's our intercept. So first of all, the regression output is going to give you the equation. It won't actually write out the equation the way that trend line did, but it's all there. Next, I want to call your attention to these three things: standard error, t-stat, and p-value. These are all very much related to each other, the standard error, the t-stat, and the p-value. They all have to do with the predictive power of your relation, the relationship between the two variables. So does this, in fact, I would call it they all have to do with the significance of the relationship between the two variables. Basically, just because we ran a regression doesn't mean there actually is a relationship between the two variables. For instance, I'm going to blow this up. You know, we could have just a cloud of data, right? I mean, we could have y and x, and our data could just look like some of those don't exactly look like points. This is going to bother me a little bit. I'm going to clean these up and replace them with actual points. The rest of it is good enough. Here's a cloud of data. Is there a predictable relationship between x and y? Not really, especially if I kind of continue to fuzz with it. No. It is really impossible to predict a value of y given any value of x. However, if this was data that I had in Excel and I ran a regression on it, it would give me a regression output. It's not going to say, "Oh, I don't think this is data," and that it would probably give me a line with a slope something like that. It would be close to 0, but it would give me it wouldn't be exactly 0, and it would give me a regression output, but it wouldn't be good. There isn't really a predictive relationship between these. So you know, we have to check and make sure there is a significant, statistically significant relationship between our independent and our dependent variables. So what you're going to be doing is you're going to be testing for that predictive relationship. Wow, my equation got so big once we the equation got so big in this when we came back to the full screen. But what we're doing is we want to make sure there is a non-zero relationship between these two variables. So what we're really going to do is run a hypothesis. We're going to do a hypothesis test here. And our null hypothesis is that there is no relationship between the two variables. Essentially, our null hypothesis is that b1, that's the coefficient of our slope, is equal to 0. And our alternative hypothesis, the one that we're sort of trying to find enough evidence to prove, is that b1 does not equal 0. There's a non-zero slope, meaning there is a relationship, a statistically significant relationship, i.e. there's plenty of evidence, we can be at least, say, 95% sure there is, in fact, a statistically significant relationship between x and y. In other words, it is a non-zero slope. And so that's sort of the way we think about the hypothesis test. And now I'm going to show you how we do the hypothesis test using the output of our regression. All right, so let's get back to the statistics given to us in our regression output. When we're looking at these, as I mentioned, the significant ones here are standard error, t-stat, and p-value. Standard error you can think of like the standard deviation for your coefficient. Meaning this is the sort of the part that we're not really sure about. There's going to be some variation in our prediction for our coefficient. And the standard error says, okay, this is sort of how much deviation there is in our prediction for that coefficient. The t-stat, that's the number of standard errors our coefficient is from 0, right? So if you divided by your coefficient by the standard error, you're going to get your t-stat. And hopefully this is starting to sound familiar to a few of you, right? I mean, we've got our standard error, which is, you can think about like the standard deviation for the purpose of this hypothesis test. And then you've got the t-stat, which is the number of standard deviations away from 0. And our p-value is actually the probability that you would have observed, you would have gotten this coefficient from your data, the coefficient for the slope from your data, if the actual slope was 0. That is, this value here is the prediction that you would have gotten that value. Basically what the p-value does is it looks up your t-stat using the degrees of freedom. So we had, I think, 20 games. We had 20 data points. And so our degrees of freedom is going to be, in this case, it's actually going to be 18. The reason for that is we've got 1 degree of freedom for each coefficient. I'm sorry, it's n minus the number of coefficients you have. So it's n is 20 observations minus however many coefficients you're using. So if you're using multiple regression, that number is going to get larger. So we'd say 18 degrees of freedom. The p-value is going to go into your a t-table with using 18 degrees of freedom and look up that specific t-stat, the number of standard errors you are from 0, and it's going to say, okay, that's how likely you would be. That's how likely it would be that you would observe this coefficient if the slope was actually 0. So this p-value is very, very small. What does that tell us? It tells us that this is a significant relationship. And in truth, all you really need to do is look at your p-value. If this were large, if it was something like 0.4, that would say we're only 60% certain this isn't this is a non-zero slope. That's probably not good enough to work with. Not any kind of predictions I'm willing to take. So you might say set your threshold. Say I want to be 95% sure. And this p-value, if it is lower than 5%, then you're going to be good to go. You're going to say, yeah, 95% sure this is a significant relationship between these two variables. I'm going to go ahead and use this regression equation to make predictions with 95% confidence. If it was actually, if your p-value was actually like 0.08, you couldn't be 95% sure. You'd only be 92% sure. That's how the p-value works. So, like I said, you really only need to ever look at the p-value, but I want you to understand how this is all working. And so I just bear with me. I want to represent this graphically. So, actually, you know what? Let's look at that real quick. I just want to show you a quick demonstration. Essentially what it's doing is setting a normal curve with the mean at 0. Because we're doing, remember, our hypothesis is that, our null hypothesis is that B1 equals 0. And we're figuring out, okay, using the number of degrees of freedom we have, essentially the number of data points minus 2 in simple linear regression, we would come up with a range for 95%. We look up in our t-table. Not necessarily 95%. It could be 99%. But let's just go with 95%. From here to here, this is negative some number, this is positive some number. And if our observation falls this many, if our t-value, our t-statistic for our observation, our observations, I should say, what we get from our regression output, falls anywhere within here, then we say, okay, we're not 95% sure this is a non-zero relationship. We can't reject our null hypothesis. But if we're out here, or somewhere out here, or heck, even out here, That's not really an arrow. But if we're out there, then we can say, yeah, sure. With more than 95% confidence, we can reject a null hypothesis, and we can go ahead and use this regression. All right, now let's look at an example. An example. A woman's clothier, I'm not sure that that's the word I want, but I'm going with it, introduces a new dress shirt into 26 of their stores at varying prices. And they're doing this to test their customers' price sensitivity. They want to measure demand, in other words, the number of unit sales versus price. So the prices of the shirt vary between $20 and $80. So at one store, they might be selling the shirt at $20. At another store, they might be selling the shirt at $36. At another store, they're selling the shirt at $80. And we've got 26 different data points, and they're measuring unit sales over 2 weeks at each of the 26 stores. So they say they set a price at a certain store, and they let it run for 2 weeks, and they count up the number of shirts they sold, and they've got 26 different data points based on this. So I'm going to need a new. I wrote that example incredibly huge, so I'm going to need a new screen here to give you a regression output. I'm not going to give you all the possibilities in the regression, all the data from the regression output, but we'll say that our B0, our intercept is 500, our slope is -5. In other words, as price goes up, unit sales tend to fall. That makes sense. Our standard error is 2. Okay. So what's our t-stat going to be? The t-stat is the number of standard errors the coefficient of our slope is away from 0. So hopefully you all said that the t-stat is -2.5. That's the number of standard errors we are away from 0. And the other relevant piece of information is the p-value. But I'm not going to give that to you now. All right? And that's because it makes it too easy. You just look at the p-value and you go, I know what the answer to this is. So let's let's draw this thing out first, just like I did a moment ago. We're essentially saying our null hypothesis never changes. It's always going to be the same. The null hypothesis is always going to be that B1 equals 0. And our alternate hypothesis is also never going to change. Our alternate hypothesis is always going to be that B1 does not equal 0. And we're always going to do sort of the same hypothesis test. And we're looking around 0. So what we can do to start off with is let's look at let's say we want to be 95% certain that there is a significant relationship between these two variables. So everything in here is going to be 95%. And so that's going to allow us, this is a two-tailed test. We can go ahead and use our t-table to come up with the significance threshold, right? The value at which, if our t-stat is outside that bounds, then we can say, yeah, significant relationship with 95% certainty, but if it's within those bounds, we can't reject the null hypothesis. So we're going to look up T, degrees of freedom. We had 26 stores. Sorry, I should have written that down. N equals 26, which means our degrees of freedom, we have 2 coefficients. We have our coefficient for B0, our coefficient for B1. It's going to be 24. So we're looking up T, 0.025, which is our alpha divided by 2, since this is a two-tailed test, with 24 degrees of freedom. So let's do that. Get down here to 24 degrees of freedom. Up here, I should probably be zoomed in a bit. Oof, gosh, it's a bit much. .24 degrees of freedom, and I'm looking at 0.025. So we get to 0.064. That's the number of standard deviations away from 0, which encompasses 95% confidence. So going back to our 2.064. Now, our standard error is 2. That's like our standard deviation. So 2 times 2.064 is equal to 4.128. So we're going to be out here at negative 4.128. And over here at 4.128. Now, is the coefficient of our slope outside this range? Are we significant here? At 95% confidence? Yeah. -5 is out here. We're good. We can go ahead and reject the null hypothesis, and we say, yes, there is a slope. The significant slope, there is a significant relationship between x and y. We can use x to predict y, and we think it is, in fact, a significant relationship. The truth is, we didn't actually need to go as far as we did here. We could have looked up that t-value and gotten 2.064, and then looked at our t-stat and seen that we're more than that. This is just the number of standard errors away from 0 that would result in 95% confidence. Our t-stat was -2.5, so we know we're outside the bounds. It's all one. Interestingly enough, if we wanted to be 99% confident, then all this, you have to sort of throw out these results. I should maybe just start over with a new table. Well, actually, I could leave -5 there. That part still works. That's still our observed value. It's -5 here. But 99% oof. Definitely should. I definitely should have made a new one. All right, well, you're bearing with me, I hope. If we look up, so if instead of 95%, if we looked up 99%, so this would be a t-stat of 0.005 and still 24 degrees of freedom. If we go into our t-table and look that up, 0.005 is significant at 2.797 standard errors from 0. I lost it. 2.797. I forgot to write 2.064 here. Well, multiply that by 2, and we're at something like, I wrote this down, negative 5.594. All of a sudden, it's farther out, and up here at 5.594. And no longer are we dealing with 95% confidence. Now we're dealing with 99% confidence. All of this is encompassed, including, you see our value, this is no longer a symmetrical normal curve. It doesn't look right, but you can see that our observed value for the coefficient is right here. In other words, we cannot say with 99% confidence that that we'd actually that we have a non-zero slope here. So 95% confidence, sure. 99% confidence, not so much. And so what we would expect to see with our p-value is something in between 0.01 and 0.05. That would sort of be that would be the expected p-value. And so let's actually use Excel to come up with what the actual p-value is. I think what we want. It's all new. I'm not familiar with. Okay, this is going to work. I'm not familiar with Excel 2013 quite as much. So I put in first my x, which is our observed. Is our what do we have for -2.5? Our t-stat. So this should actually be -2. Well, no, we'll go with 2.5. It's all the same. Our degrees of freedom is 24, and our tails are 2 tails. So yeah, okay, that's our p-value. It's 0.019. It's exactly what we would have predicted, something in between 0.01 and 0.05. So significant at basically 98%. All right, so now that we're back here, let's get back to the results of our basketball data. I'm going to go ahead and delete this. And as I mentioned before, all you really need to look at to know whether you're dealing with a significant slope and whether you're going to reject your null hypothesis and go ahead and use this regression data is your p-value. Your p-value for your intercept, I should say. So this p-value for the intercept is very, very small. It's 0.060298, the e -07. It's very significant data that we're dealing with here. So we could just go ahead and use that. The truth is, you can also just look at your t-stat, basically. I mean, it's not quite as accurate, but if you got a t-stat that's significantly above 2, you're in good shape, because that's saying we're that many standard errors from 0. And it's like looking at standard deviation. This is almost 8. If you were 8 standard deviations, you better believe you're significant. That's pretty unlikely that you would see that if the true slope was really 0. One thing I want to point out, and some of you may be thinking this already, well, look at our p-value for the coefficient of our intercept. That's not very significant. That's just 0.2. It's not even, you can't even be 80% confident. Well, the truth is, we never worry about the intercept. All this stuff for the intercept, I mean, look, a statistician might look at it and interpret it certain ways, but we don't worry about it when we're talking about the significance of the relationship between the variables. These stats in relationship to the constant, to the intercept, don't have to do with the relationship between x and y. The coefficient itself has to do with the relationship between x and y, but it has nothing to do with the significance of the relationship between x and y. That's the slope. That's B1. That's right here, and all this data relates it. So don't worry about the p-value for your intercept. Just think about it for the coefficient of your slope, whether you're dealing with simple linear regression or with multiple regression. Anyhow, now that we know that this is significant, now that we know that we can use this regression equation to make predictions, let's go ahead and do that. So, I mean, this part should be easy. Let's say we want to know what would happen. We want to make a prediction for what would happen in terms of points scored if our team shot 47%. Now, actually, if you look at our shooting percentages, we don't have any data that says the team shot 47%. But actually, we would do this even if we had data that said, if we were trying to make a prediction at 52%. We'd rather use all this data to make a prediction than just 1 point observation. So we wouldn't just say, oh, okay, last time we shot 52%, we scored 118 points. You would actually use your regression equation again, because that deals with 20 data points, which is better. So, we would still want to use the equation itself. So let's go back to 47%. Let's make a prediction based on 47%. So we start with, we'll say the intercept, and we add that to the coefficient, the slope, times the shooting percentage. And so in this case, our shooting percentage was 47%. And we would make a prediction that says, based on all our data that we've seen so far, if our team was to shoot 47%, we would expect to score 103 points. Oh my gosh, I'm going to bring this back to business. So if we know our team's average shooting percentage, we can say things like, well, if we offered a promotion where the team, everyone in the stadium gets free tacos if we pass 100 points. Well, we would know we could start to estimate the frequency that's going to happen based on, using regression. Okay, I'm probably stretching this and trying to bring it back to business. But basically, we can start making point estimates. So let's do one yourself. What if the team was really, really cold that night? They couldn't hit anything. What if they shot 35%? How many points would you expect them to score based on 35% shooting? Go ahead and do that on your own. All right, hopefully you did it. Or actually, I'm hoping you didn't do it, because I'm hoping you remembered something I said early on in this video. This was a trick question. You won't make point estimates based on, and I'm saying point estimates, this is actually the term that you would use in any kind of regression. A point estimate is where you take one x value and make a estimate for y, a point estimate for y based on that, no matter what terms you're using. It just so happened to be talking about points scored here, but it's always called a point estimate. Anyhow, you never do that when your x value is outside the range of your existing data, right? Because remember how I said you might have a linear relationship for your existing data, but it might get kind of wonky if you go outside the range, your x range? Well, if you look down here, we don't have anything at 35%. In fact, I think our lowest observation is here at 39%. So we've never shot 35%. We don't know how. We don't know what would happen it would be you could maybe make an estimate, and I'm not saying it'd be wrong, but it's much safer to not make those estimates, when you're outside the range of your existing data. So you'd say, man, I don't know, we could come up with, maybe it's better than nothing, but I'd be very, very cautious trying to make a prediction outside of your existing data. Sorry for that trick question. I'll go ahead and humor you, those of you who did the equation. All we have to do is to go back up here, substitute in 35 instead of 47, and our prediction would be 72%, but of course we wouldn't do that because we know it's outside the range of our data.